stuffing walls
With an A or with a U?
with an A. You know what is stuffing? People who provide stuff to companies. The whole industry of stuffers. And so we're going to be panelists in a session in stuffing walls.
The recruit is the company.
People they recruit, all the people, the whole industry.
He's going to give it This is
They're going to love it.
I am Bart.
This is stuffing walls. This is medical cost. This is stuffing walls.
I'm in charge of the local
So in my course and database here, I can't the middle name.
We have a
You see another account of Victor. Actually, that's where the
I'm in your radar.
So I will see what I will.
Well, just as much for it.
And then you can see how the character comes exactly. Things like
we also have the young people sets of
so anyway, there's no one paying because of your time. So let me
half an hour slots on that Peter Sellinger is on Thursday. So thank you for coming back.
okay.
So we continue this morning with Professor Bart Selman from Cornell University, who will speak about Fourier representations in probabilistic inference.
Okay, thanks, and thanks for having me here. So this is about Fourier representations for probabilistic inference. I should point out it's really the work of one of our students, Ye-Sheng Xu, who I think has one more year to go, but he is really the main driver force behind this new work. So, and I guess other people, Stefano Ehrman, Ronan Lebras, Carla Gomes, and myself. So it all starts off with sort of thinking about probabilistic reasoning, and of course the key observation that people use in probabilistic inference is to have some high-dimensional probability distribution, but be able to represent it in some compact form. So this leads to the vector graphs and graphical models, etc. And this compact form allows then for efficient inference algorithms and machine learning with better predictive power and generalization, if you find the right form, okay? And all these representations are based on some form of independence, and you know, here's just the most extreme form of independence where you can write a joint probability distribution as a product, but of course there's conditional independence and all kinds of different forms of independence. What I want to advocate in this talk is to use a Fourier representation of what we call Boolean, pseudo-Boolean functions, which are really probability distributions. But we proposed it as a novel way of representing a high-dimensional probability distribution. So my goal is to sort of give you a flavor of what the Fourier representation can do for you, and some results on why it is a good representation, and finally some experimental results showing it works very well in practice. Okay? So the two key points I'm going to show you is Fourier. You probably have seen some form of Fourier analysis in continuous domains. We're in signal processing, where you look at the Fourier spectrum of a signal. One thing we're going to show is that for interesting probability distribution, most of the probability mass concentrates on lower degree coefficients in the Fourier spectrum, which means Fourier spectrum can actually have an exponential number of terms, but we'll be able to cut off to the first small polynomial number of terms and get a good approximation of our distributions. And in fact, what we'll do in the algorithms, we'll actually drop higher order Fourier coefficients. And the nice thing about that is we can do that and give good approximation in terms of L2 norm with respect to the full distribution, and we'll get some approximation guarantees, which are much harder to obtain with other methods like variational approaches or mini-bucket elimination, which are inference procedures that give bounds, upper bounds or lower bounds, but generally don't give a clear L2 norm approximation. So these are the two main properties I want to bring out. And then we'll have the orders of magnitude on a practical evaluation. Okay, so very basic introduction. So let's say we have a little factor of just two variables. All variables are Boolean. We use -1 + 1. So -1 to represent false, +1 to represent true. And we just have a little function here of two variables. So 4 possible settings. And these are the real values. Think of these as four numbers, probabilities that add up to 1, for example. Now, what we can do, so normally in inference, these are probability tables, messages when we have message passing algorithms, or little probability tables that are moved around. But we want to represent this function differently. We want to represent this function in Fourier representation. I'm just going to show you how you can get the Fourier representation. Although it's just for a two-variable case, but it generalizes. This is a linear interpolation formula. You can see that every entry here, so we rewrite this function phi xy into this form. And if you just look at the first entry, -1, I'll put in -1 here, 1 -1 -1, this evaluates to 1. This evaluates for -1 to evaluates to 1. And so basically in this first row, you see that this expression evaluates to phi 1. Okay? And actually the other ones will all evaluate, that's the green parts. And one of them, 1 - 1, with y -1, will get to 0. So all the other terms disappear. And similarly, you can check for all other settings that this expression is the same as this function. Okay? And then you can, again, rewrite this, group the terms, and you get terms as a function of x, as a function of y, as a function of x times y, and the 0 term here with no x and y. So this is the Fourier representation of this little function here. So x, y, and these are the Fourier coefficients. This is the first Fourier coefficient. This is the first degree term. Actually, here is the basic function x, and we have a basic function y and a basic function xy. These are the Fourier basis function, and this is a value, a real number, basically, the coefficients, the Fourier coefficients. Okay, so this is a very tiny example. In general, it's called the Hadamard Fourier transformation. Every weighted function can be uniquely expressed as a multilinear polynomial, where these are the Fourier coefficients and these are the Fourier basis functions, which are basically products of x, y, z, etc., products of the original variables. And these products are actually parity functions. I'll give a little bit more detailed example next. So actually, let's just skip to that. So here's the example I just had up. So this is actually the 0 degree term. This is the first degree term. It has a Fourier basis function of x. This is another first degree term, Fourier basis function y. These are parity functions, x, y. Why are they parity functions? Well, they're products of x, y, and evaluates to -1 if an odd number of variables is set to -1. Okay, so that's why it's a parity function. These become x, y, z, very long sequences, up to full length products. Okay, so we're rewriting the original function in this Fourier form. Here we just have up to degree 2 because we just have two variables. Okay, so and all the coefficients are just real numbers. Okay, so let's think a little bit. Why are we doing this? Well, the general representation is just of the original distribution is just a table of 2 to the n entries, starting with all -1s to all +1s, 2 to the n numbers. Our Fourier representation will actually also be an expression in general of 2 to the n numbers, because these basis function can go all the way to a full product, basically all subsets of variables. Each subset of variables correspond to one Fourier function or one Fourier basis function. So, we have 2 to the n terms. So, on the surface of it, of course, we're not actually making any gain, and we could basically dismiss this. But why do it at all? Okay. So, what I want to show is that this representation, as opposed to the table representation, many functions will have a few lower order terms. That is all that's needed. So you don't need these very long parity constraints. We can just do with 3, 5, maybe 6 variables. You don't have to make very long products of variables. And the second part is you can truncate it, set all the higher order terms to 0 coefficients, and then you're guaranteed that this thing still approximates the original table quite well in the L2 norm. Okay, so. As just for the continuous case, just to show now, this is sort of totally analogous to the continuous case for Fourier representations. So if you have a continuous signal, you can approximate it, if this was your original step function here, you can approximate it by a summation of these sine functions, and it gets better and better. So the first approximation, just the first degree 1 approximation of sine functions, but you get higher and higher frequencies. But the key thing is that the coefficients of these frequencies, the higher frequencies become smaller and smaller. Okay, and we want actually most of our, they call it the power spectrum, most of our coefficients, we want to be focused on the first few Fourier functions. And so this happens in the continuous case, for many signals, and it's also going to happen for the discrete case. I'm going to try to give you a bit of an intuition why that is, but I'm not sure I'm going to succeed at that. So there is another way of looking at the Fourier coefficients, and that's written here. So this sum is actually key. It's a sum over. So the parity function, that is that product of x, y, z, etc., corresponds to a hyperplane in our space. And the hyperplane is going to divide the function points into function on the right and on the left of the hyperplane. Okay? And the Fourier coefficient now is going to be a sum over the points, the function values that lie on one side, minus the function values that lie on the other side. And you can show that formula is equivalent. That formula defines the Fourier coefficient. Okay. So, but I just want to not go look at the math. Sort of more thinking of you have this high-dimensional hypercube. You're going to put a hyperplane through it, separate your two sets of points, and you sum one up, and you sum another one, and you look at the difference. Okay. Now, so the Fourier coefficient is the difference between the sum of the values. Where one side of the hyperplane and the other side of the hyperplane. Okay, and so what we're going to have is that if you have a long parity constraint, the separation is sort of like a random cut through your space, will roughly give even weight to both sides. So these points will, the total weight on this side will be roughly the same as the weight on that side for a long parity constraint. And because we're taking the difference, the coefficients will be almost 0. And that's actually sort of interesting because I guess Stefano Ehrman will talk later, I think this week, tomorrow I think, about counting an inference using these parity constraints. And in that work, we're exploiting the fact that long parity constraints sort of randomly cut through the space in a balanced way. We actually want that property. Here we're just saying that property gives us near 0 Fourier coefficients, okay? Yeah?
Question. So if the function f happens to be the parity function of all the variables,
then
this fails.
Yeah, then it doesn't work. Yeah, it doesn't work for all functions. Yeah.
There are some practical assumptions about what these functions are that prevent the parity from.
Yes, and well, actually, you'll see that very good. We'll see that in the next slide where we prove something about what we want from a function. The parity function is indeed a bad example for this thing. Okay. Yeah, very good. Yeah.
the parity function is also, you know, that theorem about Boolean circuits that separates shallow circuits from deep circuits.
Yeah, exactly. So our proof will be based on Hastad's switching lemma that actually exploits that property. So yeah, so that comes out of the Boolean function work. So I'll show in a moment. Okay. So yeah, so if your function is a single long parity function, that all the coefficients will go for that parity function. But let's hope the world is not like that. Okay. So most high order correlations are rare. Okay. Therefore, the weight difference of the Fourier corresponding long parity functions are usually small. Another way I like to say that the Fourier exposes small groups of variable interactions. If your probability distribution indeed is based on small sets of variables that interact and that they have the most effect on the probability distribution, the Fourier coefficients will bring that out, okay? And that's what we're hoping for. Let me skip to this next one. As I said, we're going to at some point drop higher order terms. And so to do that, we're actually going to introduce a notion of a Fourier spectrum being epsilon concentrated on degree up to k. Look at the degree of the parity function up to some length k, and then look at the sum of of all the coefficients on the higher degree terms. Okay, and we say a Fourier spectrum is epsilon concentrated on degree up to k if this sum is not too big. If this sum is actually quite small, less than some small value epsilon, okay? If that's the case, we say the Fourier spectrum is concentrated. And this is, of course, the kind of Fourier spectrum we like, that has little over here. But I guess it's not always the case that it's the, but now. So let's see what functions, so what I'm now claiming, and that's sort of the central technical result. The tail bounds lead to good approximation. When the Fourier spectrum is epsilon concentrated, we can drop higher order term and get a good guaranteed boundary accuracy of the approximation until to distance. So we can actually drop if our function is like that this is very small, we can drop them, get a good approximation. That proof actually is not that hard. It's formally, but I'm not. I don't want to go into the formal details, but that's a fairly straightforward thing to show. Okay, so that's good. We can get rid of the higher order terms. This is the more interesting result, and way harder to prove. So many interesting distributions have bounded degree Fourier spectrum, have this low tail with very low probability mass. Okay, so formally, let me just bring up a little picture. Okay, so if your probability distribution is of a certain form, so you have a few terms, a few values that are 1 or can be normalized to 1, and you have a bit of a gap between those values and the second lowest values. So this gap, there should be some gap here. If we have that gap in our distribution, we call it the contective gap with gap 1 minus epsilon. This difference is 1 minus epsilon, so that's the gap difference. If your distribution has that property, so there's a gap between the maximum and second value and the second level values, then we can prove this result. And I will not say all the details of the result, but we can show that the Fourier spectrum is epsilon concentrated for factor graphs of some bounded width. That means the factors have a certain maximum number of variables in each factor. Okay. Now, to prove this was not easy, but it comes from extending results, and this is related to the Boolean function observation of the Hastings switching lemma, where it's used to show lower bounds for Boolean functions. It's a very nice result showing that if you take a CNF and you randomly set some variables in that CNF, then with a good probability, the remaining formula becomes a small decision tree. And the proof now shows that small decision tree can be written with a few Fourier coefficients of low order. Okay, and we can bound the probability of it going wrong. So we can show that the fraction of cases where there's no small decision tree remaining is vanishingly rare. Yeah.
How do the preconditions here rule out the parity function?
That's a good question. I would have to actually look at that. It should, but I have to look at it. Yeah.
Can you explain exactly bounded width? Because it hasn't been...
Bounded width is just, actually that will do it, yeah. It has to be bounded width. So each factor, so think of your probability distribution as a factor graph. Each factor has only up to k variables in it. That's bounded, and that answers your question. I like that. Yeah. Luckily. Bounded width, so it's only up to some width k, so you can't do large parity functions. Okay? And so, was there another comment? Okay. So, and I left, Yesheng had the full proofs, but I was actually decided to spare you the details on a number of slides, and I've deleted those slides. But it's a clever construction. Of course, the Hastings switching lemma by itself is a very nice result. So generalizing it to these pseudo Boolean functions is an interesting way of doing it. And the key thing is you get to these, after your random restriction, you get to these small decision trees, and small decision trees it's not hard to show, they have short, they have Fourier coefficients of low degree, and that's what we're exploiting, and that's what Yesheng did for this result. Okay. Okay. So. Since we don't have the proof, we'll just go on. Ultimately, we want to use this, or we did use it in variable elimination, in inference reasoning strategy, and we're actually going to use it to calculate partition functions. Now, we're just going to use. So we're going to represent, during our calculation process now, we're going to represent probability distributions in the Fourier domain. But while we're doing it, the algorithm now and then drops higher order terms. And because of these result of approximation, that's still a good approximation, we can do that. Okay. So very, very quick little 101 on variable elimination. So you have your factors here, and you want to compute your sum of these function values over all settings of A, B, and C, and D. And a variable elimination strategy starts doing it by picking a fixed order on your variables and then eliminating variables in your sum in this order. Okay? So a very little example, we can eliminate A by looking at the terms that have A. Okay, you get this sum. We rewrite it as GBC because we have summed out the A value, and then we work with the sum on a reduced number of variables. Okay, that's a very basic strategy. It's of course exact. The problem is if you have, let's say A occurred also in F, A, and D, so in more factors, then these new functions start growing and growing. So they have more and more variables, you get larger and larger tables. So in inference, that's the problem. That's the problem in exact inference, that these sub-results start becoming larger and larger sets of values. Okay. This is actually not a good example because here we only have two variables left, but in general, imagine you have F, A, comma, D here, then you have G, B, C, and D, and etc. So these things start growing. So a lot of the approximation algorithm, or a lot of inference algorithms like mini bucket inference approach by Rina Dechter, limits the size of the size of these tables by truncating them effectively. Okay, we are not going to truncate these tables. We're going to use the Fourier representation and drop the higher order terms. Okay. Okay. So we're actually going to do two things. The tables become too large in general inference. So we keep the Fourier representation, and we looked at two different ways. One is just keeping the lowest order terms around, so don't have high parity terms in our inference, or look at the terms that have the highest absolute value, and so only keep the Fourier coefficients around that have high values. And because of the weight concentration of the Fourier representation, removing the higher order terms should preserve, will give us a guarantee in L2 distance with respect to our original distributions. Okay, so let's just give the results. Okay, so this was a UAI inference challenge, and the idea is to calculate partition functions. I don't quite know what are the names of the problems, but this is the mini bucket algorithm, and these are Fourier results. We look at the absolute difference between the log 10 of our approximation of partition function, that exponential sum, minus the exact value. So for this challenge problems, they do have a ground truth. That the problems are just of the right size to be able to do the ground truth. Can be done in 2 hours with an exact method. So we know the ground truth here, but these results are all computed in minutes. Okay, so that's sort of the contrast. The exact method, 2 hours. These results obtained in minutes. Okay, but look at some of the differences. You see things going, from 26 down to 10 to the minus 3, 5 to 10 to the minus 6. So these differences between the true values and the approximations become very, very small. Okay, we looked at a number of this is belief propagation.
So, I don't quite understand. Mini bucket is the exact value.
No, sorry. Mini bucket is also an approximation. Yes. Yeah, it's an approximation. So the exact values would all be 0. We compare it to a true value for the approximation.
So here you have, let's say, the fixed of 3.91.
Yeah.
And then you have two numbers on the Fourier. What's the relation? How should
so 3.191 is the, so we're looking at the log base 10 of the approximation result obtained by mini bucket minus the log base 10 of the true value. And we take the absolute value of that, okay? And that is 3.91, okay? If they were the same, this would be 0.
I see.
Okay, so this becomes...
the quality of the approximation.
Yes, the quality of the approximation, and we want the number to be as small as possible. Ideally, we want it to be 0, okay? Yeah. So smaller is better, yeah, exactly. Yeah, and again, so these are problems where they can just, for the challenge, they needed to have the ground truth. So this is problems where you can just get at the ground truth. We have other results in computer vision and some other applications where we no longer know the ground truth. But I find that it's always a little hard to talk about it because we don't quite know how good the approximation is. Yes?
How did you choose the elimination order?
I don't think anything's actually. I don't know. I guess that we would have to ask Ye Sheng. So, I think he didn't do anything particularly special. Yeah, it's some heuristic. Yeah. So probably the same as mini bucket picked. Yeah. So, okay. Yeah. So we see these numbers. Again, so as close to 0 as possible, that's what we want, okay? And we see slight difference between if you take the maximum coefficients versus the minimum, only the low degree terms. I think this is slightly better than this one. The bold ones are the best numbers we got. So these are all approximation methods, by the way, okay?
What is HAK?
So HAK, we'll go there. So HAK was the award-winning solver, I think, of 2 years ago or last year, which was a portfolio of state-of-the-art solvers. So I think variational methods, and really, I think it picked the right variational method,
Yeah, so it will beat you, right?
Exactly. Yeah.
What happens with MCMC?
MCMC, I guess it found the probability of the configuration it got were so low that it didn't find any reasonable probability. So it's a little odd, but yeah. If you have some hard constraints or some extreme probabilities, MCMC actually has trouble finding any good states. And belief propagation, actually does reasonable in some values, but then gets pretty bad here. So we were quite encouraged by this because it really is the best approximation by several orders of magnitude. And the reason the student Ye Sheng thought of this, I guess he worked for a while with his mini bucket approach. This is an exact algorithm, but when tables get too big, there's some heuristic of how to prune the table. And he looked at that and said, that's not a very principled approach. The Fourier coefficients is a much more principled way. You drop higher Fourier terms. And that intuition comes out that they're doing similar inference strategy, variable elimination strategy, but better approximations of the intermediate distributions. Okay? And that's it. Okay, so okay, good. So I hope I have given you some idea that this Fourier transform representation can be very useful to do high-dimensional probability distribution and can give compact representations. Number of nice properties. We could show that for vector graphs is limited with factors. The probability mass does concentrate on low degree coefficients. Very nice proof here, the Hastings switching lemma. And we can also can show that if you drop the higher coefficients, you still have a good approximation L2 norm, assuming that the tail is not too fat of the higher order coefficients. And then finally, a validation by actually doing this evaluation on the UAI challenge problems for partition functions and going and seeing how you get much better approximations than the other methods. And that's it. Thank you.
Questions?
Yep.